So today we're going to start our new unit on forces. So we're going to talk about various forces and how we describe or show them acting on an object. So some key vocabulary that we're going to be using. So a force is half of an interaction. So normally we think of a force as a push or a pull. So acting on an object or the object's reaction to that force. So the unit for force, we're going to measure it in newtons, named after Sir Isaac Newton, capital N for the unit. We usually, when we're drawing diagrams, we want to show forces acting on an object. So we use arrows to show these forces. We call it a force vector. So vector meaning it has both a size and direction. So the arrow is going to tell us both of those things. So the size of the arrow represents how much force is being applied. So a longer arrow means more force. A smaller arrow would mean less force. And then the direction in which the arrow is pointing is how the force is acting on that object. So is it pushing it to the left, to the right, up, down? So those arrows are going to show how the force is interacting with an object. So we're going to talk about the various forces that can be drawn with these arrows, and then we'll practice drawing some of those diagrams at the end. So force, half of an interaction, a push or a pull, measured in newtons. So there are kind of two main groups of forces. So the first group is called an applied force. So meaning you have to make contact with the object in order for it to apply the force. Sometimes it's called a contact force, is another name for it. But in general, this is the most common type of force we think of when we are talking about forces. You have to come into contact with an object to get it to move. So you apply the force to it. So when we're drawing our diagrams with our arrows, we want to label what this force is. So the symbol for an applied force is F for meaning force, and then A for applied. So F sub A. So if we ever see this symbol on a diagram, it's talking about an applied force. So there are a couple different types of applied forces that we will come across. So first one is tension. So if something's hanging from a string, a rope, or a cable, or being pulled by a string, rope, or cable, we call that a tension or a tension force. So there's two symbols we use for those, so make sure you have the symbols down. So Ft, or simply just a T for tension. Another common force that we're going to be drawing in our diagrams is friction. So again, the surfaces have to come into contact in order for friction to be applied. So friction always acts opposite motion. So if we're moving to the left, our friction is to the right. If we're moving to the left, our friction is to the right. So it's always opposite the direction our object is moving. So the symbol for friction is F sub F, so force of friction. And then the last force that we have is called the normal force. So the normal force acts to keep objects apart. We can also think of it as a force, and I want you to write this definition down too. So it's a force that is always up when we have an object on a surface. I think this definition maybe describes it a little better. So if we're sitting in our desk chair, why don't we fall through the chair? Obviously, gravity pulls us downwards. Okay, but it's a normal force that pushes up on you. So the chair pushes up on you. So the normal force is always going to be up when an object is on a surface. So if we're standing on the floor, okay, so gravity pulls us downwards, normal force is pushing upwards on us. Or if we have a book sitting at our table, so there's a normal force pushing upwards on that book to keep it on the table. So the normal force that keeps an object apart. And so the symbol for a normal force is F sub N. So it's always going to be upwards if we have an object on a surface. Okay, so the other kind of classification of forces are field forces. So an applied force is a force that you need to come into contact with the object in order for the force to be applied. But a field force doesn't need to come into contact with an object to apply that force. So the big common one that we all are going to talk about is gravity. So you do not have to come in contact with the earth or an object, if we're talking about in outer space, in order for gravity to be applied to that object. So no contact is necessary. So the gravitational force is always going to be pulling you downwards on Earth, but you don't have to be in contact with Earth in order for it to be applied. So, but it doesn't have to be Earth. So any object, they're going to attract one another. So it's the force of attraction between all objects with a mass. And so the symbol for gravitational force is Fg, force of gravity. When we're talking about Earth, we give it a specific name. So your weight is actually your gravitational force. So it's the force of Earth pushing down on your mass, which is your weight. But again, remember, it doesn't have to be touching. So it's a field force. So the Earth pulls on the moon pulls on the Earth. Those are both field forces. So gravity is acting there. So let's take a minute here and see if we can classify them as applied or field forces. So I'm going to write an A or an F over top of them if they're applied or field. So gravity, we just said that one was a field force. So we don't need to come into contact with our object for gravity to be applied. Pushing a cart, so that would be an applied force. You have to contact the cart in order to get it to move. Your weight, remember we said weight was the force of gravity. So weight is a field force. How much gravity is pushing downwards on you. Kicking a football, so that would be an applied force. So your foot has to come into contact with the football in order for it to move. Friction. Friction is also an applied force. So your foot or your on the ground have to come into contact, or the tires of your car and the ground have to come into contact in order for friction to be felt. Obviously, an applied force is an applied force. Static electricity. So that would be a field force. So if you've ever kind of played around with like little pieces of paper and a charged balloon, the paper will actually come off the ground and attach to the balloon. So they don't have to come into contact with one another for it to be felt. Normal force, remember that's the force of an object sitting on a surface. So they have to be in contact in order for a normal force to be applied. Pulling a wagon, that would be an applied force. So you have to pull on the wagon, or you have to touch it, come into contact with that wagon in order for it to be felt. Magnetism, so that was a field force. So if you bring magnets close enough together, eventually they'll pull together or they'll push apart. But they don't have to contact one another in order to do that. Okay, air resistance. So an object is falling through the air. So that's an applied force. So you have to touch the air. If you move your hands back and forth, you can feel the air. So you have to come into contact with it in order for it to be felt. Okay, hitting a baseball. That is an applied force. So the ball and the bat have to come into contact in order to make that force to be applied. And then tension. Tension is an applied force. So you have to pull on the rope, or the rope has to be in contact in order for it to be applied. Okay, so remember, applied force requires contact. Field force requires no contact, so it can act over a distance. Okay, next let's talk about how we show these forces acting on objects. So we draw something called a free body diagram, FBD for short. And so a free body diagram is going to show just the forces acting on a single object, and only the forces that act on the object. So that's why we call it a free body. So we're freeing it from everything else in the situation. We're just looking at that single object. So we represent that object in these diagrams by a dot or square. And then we use arrows to represent how the forces are acting on the objects. So remember, the size of the arrow is representing the amount of force applied. So a longer arrow means more force. A smaller arrow means less force. The direction of the arrow tells you the direction the force is pushing on that object. So up, down, left, right. And then the symbol, the force sub N, remember, is normal force, applied force, friction, or gravity, working on that object. Sometimes we write the words out if it helps you remember what they mean. So free body diagram. So we're freeing it from all the other situation that it's in, just looking at that single object. So let's practice drawing a couple. So a ball is falling downwards through the air. We want to draw a free body diagram for this object. Okay, so I'm just going to draw my object with a circle in the center. And I'm going to draw in the forces acting on the object. So what force would be pulling it downwards? So downwards would be gravity. Gravity always pulls you down towards Earth. So I'm going to label it F sub G for gravity. Next, I'm going to show some other forces. So pushing upwards on the object, slowing it down slightly, would be our air resistance. So again, it should be a smaller force because gravity is larger. We're moving downwards, so that force should be greater. So I'm going to just call it F air, or we could put FA for an applied force. Might be a little more specific. Any other forces acting on our object? And there shouldn't be. Gravity pulling it downwards, and we're moving downwards. That should be a bigger force arrow compared to the air resistance pushing upwards. Okay, let's try another example. So a book is being pushed rightwards across the table. Draw the forces for the book. Okay, so I'm going to draw my object in the center here. And now we have a rightward force. So I'm going to arrow pushing towards the right. And I'm going to call that applied force. So we're applying it to the book. Okay, there has to be some force opposite that. So opposite motion, the book is going to experience some friction. So F sub F. It should be smaller because we're moving to the right, so we have a larger applied force than we do friction. If all the arrows would be equal, that means our object is not moving. We always have gravity pushing downwards on the book. So force of gravity, Fg. And our book is not moving down to the right, so we need some force opposing it. So as it sits on the table, there should be an equal force to gravity. And that's going to be our normal force. Remember, any object sitting on the surface has an upwards normal force. So it's normally there. So the arrow should be equal. Force, normal, force, gravity are equal because we're not moving up and down. We're only moving to the right. So we want our biggest arrow to be to the right. Okay. So gravity is always there. So you always have to make sure we have gravity in our diagram somewhere. Okay, let's try another example. So a book is at rest on a table. We want to draw the diagram of the forces acting on the book as it sits at the table. So I'm going to draw a dot in the center to represent my object. So as it sits on the table, we always have gravity. So gravity is pulling the book downwards. So force of gravity, F sub G. Now we're not moving downwards, so we need some opposing force that should be equal in size to gravity, so equal length arrows. Remember, as an object sits on a surface, we have normal force pushing upwards. No other forces because we're not moving. So gravity is always there, so we have to have that normal force pushing upwards on the book because it's not falling through the table. It's sitting on a surface. So we kind of hinted at forces being equal or forces not being equal and our object being unmoving. So we can give this a name. So our free body diagrams help us to determine if there's a net force. So a total force on an object is our net force. If all the forces are balanced, we say our object is at equilibrium. So our net force would be 0. So like a book resting on a table, all the forces were equal. So our book was at rest, not moving. So the net force was 0. Everything cancels. like in our pushing the book across the table, we had a bigger arrow pointing to the right. So our net force would have been some value to the right. So we would have an unbalanced force. So it would not be at equilibrium. So if we're at equilibrium, everything should be equal. And our net force would be 0. So here's an example of a balanced force. So our net force on the object is 0. So let's say student A pushes with a force of 2 newtons. And student B pushes with a force of 2 newtons. But we're going in the opposite direction, so we get a negative sign. So 2 plus a negative 2, or 2 minus 2, gives us a net force of 0. So our box will not move. So having balanced forces means all forces cancel, means there could be no movement, or that we're moving with a constant velocity. So we're not gaining speed, we're not losing speed. So all the forces are equal. Okay, so let's look at when they would not be equal. So we would call these unbalanced forces. So here our net force does not cancel out. And this would cause a change in motion. So that means we're going to accelerate, we're going to move faster, or we're going to slow down. So we have some acceleration when we have an unbalanced force. So if we look at this example, let's say this student pushes with a total of 5 newtons to the right, and this student pushes only with 2 newtons back to the left. So we would have a net force of 5 plus a negative 2, or 5 minus 2. So our net force would be 3 on this box. And it would be 3 to the right. So remember, we think of right, up, east, or north as positive values, and our negative values are left, down, west, or south. So always remember that. And so unbalanced forces, we're going to have a change in motion, and we're going to speed up or slow down. So we're going to have an acceleration. Let's look at a couple more examples. So are these forces balanced or unbalanced? So here we have a car. You can see the spacing gets more and more apart. So that means we're accelerating. So is that balanced or unbalanced? That's going to be an unbalanced force. So if we're accelerating, if we're changing speed, we have an unbalanced force. Okay, let's look at the next picture. So our spacing between them is pretty constant. So that means we have a constant velocity. So constant velocity means we have a balanced force. And then lastly, here we have the spacing that's getting closer and closer together. So we're slowing down. Our speed is changing, so that's unbalanced. So if we're changing speed, we're accelerating or we're deaccelerating, unbalanced forces. If we have a constant speed, our forces are all balanced. Okay, last let's talk about some problems that will be similar to your homework today. So we have some descriptions here of a situation. We want to draw our free body diagram, and then we want to figure out what is the net force on our object. So here we have a book that's being pushed across the table with a force of 5 newtons to the right. So we have our object being pushed to the right, and we're actually going to label it our applied force, and we're going to put the value of it. So I'm going to write 5 on the arrow. Then we have the frictional force, that is 2 newtons to the left. So smaller because it's not as big. And it is my frictional force, so F sub F. And it has a value of 2. Okay, we have gravitational force that's downwards on our object of 10 newtons. So force of gravity. And then we have the normal force, which is pushing upwards with the same value, so same length of our arrow. So Fn for normal. And that again has a value of 10. So we want to find what is the net force on the book. So up 10, down 10, those are going to cancel. so we don't have to worry about them. So then we're left with 5 and 2 on our left to right direction. So to get our total force, our net force, we're going to take 5 plus, remember going to the left is considered negative, so 5 plus a negative 2, or 5 minus 2 is going to give us a net force of 3 newtons. Okay, let's try another example. So net force of 2, example 2 for net forces. So here we have our picture already drawn. So we want to find the total force acting on this object. So here we have tension upwards. Remember, upwards is positive, downwards is negative. So we have a negative 800. So 1200 minus an 800 gives us a net force of 400 newtons. Let's try example number 3. So here we have an object. Looks like we have some gravity working on it and some friction. So let's look at anything that cancels. So gravity and normal force, up and down, would cancel because they're both the same value. And then we're left with just this 20 newtons to the left. So our answer in this one, really easy, is going to be negative 20 because it's to the left, and newtons would be our net force. Okay, and then the last one, let's look at just some arrows. So if we're looking at this first one, 5 and 5, both in the same direction. So they would add together to give us a net force of 10 newtons. Here we have 5 to the left, 5 to the right. So we get a net force of 0. Okay, so this one is going to be unbalanced. This one's going to be balanced because we have a net force of 0. Okay, 5 plus 10, so they're both in the same direction, so they add together to give us 15 newtons. So that one's going to be unbalanced. 5 plus a negative 10, so we're going to get a negative 5 newtons. So again, unbalanced. We have 5 plus a negative 15, so we're going to get negative 10 newtons. Unbalanced again because we don't have a value of 0, so we need 0 in order to have a net force to be balanced. And then up 10 and down 5, so we get a balanced or unbalanced force of 5 newtons. And last one, which of these objects are moving? So study the diagrams and figure out which of them are going to be moving. So to know if an object is moving, we have to have some unbalanced forces. So let's look at situation A. Anything cancels. So we have up 3, down 3, that cancel. Left 5, right 5, that cancels. So we have an object that's not moving. Okay, let's look at this one. Up 3, down 3, they cancel. But here we have 5 that doesn't cancel. So this one is moving. Let's look at C. Up 20, down 20, cancels. So not moving. And last one, we have up 40, down 25. So they do not cancel. So this object would be moving upwards. We have a bigger force pushing upwards on our object.